Okay, so we will get started. We are pleased to have Nishino from Drexel University. He got his PhD from Convey University, then he did a postdoc, several years Columbia and Nishino. So he has done interesting work in reflectance and 3D, and more recently has been involved in ground analysis also. So he's going to talk about visual material recognition. Cool.
Thank you. Thank you, Mrf, for the invitation and letting me give a talk here. So I'm Nishino from Drexel University, and today I'd like to talk about visual material recognition. And before I start that, let me introduce and thank my past and current students. And these are the guys who did the actual work. And today I'd like to highlight the work done mainly by Steve and Gabe, sponsored by ONR and NSF. Okay, so why should you care about visually recognizing materials? Or in other words, why would you want to actually tell what an object or a scene is made of just from its images? Now for that, let's just imagine taking a walk in a beautiful autumn day in Kyoto, and you wander into this temple that has these stone stairs leading up to the main hall covered with these Japanese red maple leaves. Now, you as a human being have absolutely no problem at all finding your way up these stairs while you crush on these leaves, right? But think about doing the same with some kind of an autonomous system. The system needs to deduce at least some properties about the scene. For instance, the fact that these red things are actually soft and fragile, that they can actually step on them to get the support of the hard stone stairs, right? And that's information pertaining to the material, right, of the scene. And ideally, you would want to know such material information without knowing what the object is, because object recognition is a really challenging problem on its own. And in fact, object information, that's object recognition basically done on shape cues, encoded in the shape cues, can be very deceiving. For instance, you can have these cases where your book turns out to be made of ham, and your table is actually made of aged cheese, and your alley is paved with these wheat bread, and the tree line is actually broccoli, right? I just had to find a reason to show you this cute foodscape. And you can Google Carl Werner's name on the internet to see a lot more. But really, trying to identify or extract material information, regardless of the object, is actually a very important requirement. Because, for instance, imagine asking your personal robot 10 years from now to put a wool glove on your hand on a really cold day, which I think doesn't happen here. But for that, the robot actually needs to tell that one is made of leather, one is made of wool, one is made of skin, despite the fact that they all look like hands, right? So that it can actually pick up the wool glove and put it on your hand instead of ripping your hand off and stuffing it to the leather glove, which is wrong in many ways, right? So it can even affect your health, right? And of course, you can have these extreme cases where material is the only factor. Everything other than the material conspire to fool you, right? And even in such cases, you would want the computer to actually recognize the material so that you or the system can make reasonable choices. And if you really think about it, there has to be some information embedded in the images that hints at the materials, because we as human beings can actually look at this and say that, okay, this Obama is probably not going to respond to a request of a handshake, or we can guess that if I bite into the sushi, I might lose my teeth, because it actually is an iPhone case, right? So really, the goal here is to uncover and extract that untapped visual information pertaining to the material of the scene to help higher level scene understanding tasks, to understand the scene better. Now, of course, I'm not the first one to argue about the importance of recognizing materials. Ted Adelson from MIT had this great paper in 2001 that argues for the vision community to really look into recognizing stuff, that is materials, in addition to tackling this hard problem of recognizing things or objects. And really the challenge lies in the fact that the appearance of materials are instantiated as a result of a combination of a number of factors ranging from intrinsic mechanics like the viscosity to the extrinsic optics like the lighting and the viewing directions, right? And we as human beings can sometimes even recognize things at this level. For instance, you can look at these images, this image, and maybe tell that the left one is skin cream and the right one is cream cheese, swirled by the same knife motion, right? So you can actually decipher things even up to this level, how that shape was actually instantiated. But trying to make a computer decompose an image into all these factors is just a bleak endeavor, right? But the key is that you just have to extract just enough information that's unique to the material to tell what the material is. So I'm going to talk about two approaches today. One that tries to extract what the intrinsic optical properties of the material is from an image, and the other that directly tries to work on images. Okay? So the first approach is going to be a generative one, where we basically try to undo the image formation process so that from a single image, as few as a single image, we can extract and estimate the building blocks of the appearance, namely the geometry and the material as a reflectance and the illumination. And the hope here is that the reflectance will tell us what the material is, right? And obviously this, what we call the radiometric scene decomposition problem, is a very severely ill-posed problem, and the main focus here is going to be about how to tame the variability of real-world reflectance. Okay? And the second approach is going to be a discriminative one, where we directly try to classify each pixel into different materials, right? And here, the focus is going to be on finding ways to tame the appearance, the interclass variability of material appearances. So let me start with the generative material recognition approach. Okay, as I said, the goal here is to take a single image and decompose it into the reflectance, geometry, and illumination. Okay, those are the building blocks that make up that appearance of that particular object. And we call this radiometric decomposition. And if we can do this radiometric decomposition, we can put all that information estimates into whatever material recognition or object recognition method. And in fact, many of the long-standing problems in computer vision can be thought of as specific instances of this radiometric decomposition problem, where in many cases we try to estimate one or two of the three factors, right? But most of these works heavily rely on a very simplistic assumption about the reflectance, for instance, Lambertian reflectance, that says that light is reflected uniformly in all directions regardless of the incident light ray direction, or instead require an impractical amount of input images. Now, what we really want to have towards generative material recognition is the ability to recover the reflectance, especially the reflectance, with potentially unknown geometry and illumination from as few as a single image. And that's definitely a severely ill-posed problem. And one thing that you notice is that the reflectance acts in a very special way, as it defines how the incident light ray interacts with the geometry and forms that image, right? So trying to do radiometric decomposition actually means recovering that function itself from an image. Okay, so there's no wonder that people have heavily relied on really simplistic models like Lambertian, which is linear. But what we really want to do is, as such simplistic analytical models do not really do much faith to the rich variation of our visual world, we want to have a simple but analytical expression that can express all sorts of materials, like all these 100 materials, but at the same time lets us recover that from the images, right? And that's really a tough problem. But if you really look at all these materials, that you notice that the real world reflectance of materials are not arbitrary. There's some coherence, right? There's some similarity in the way that they're glossy, that they're diffuse, and so on, despite the differences in the colors, right? So what we really want to have is a model that can actually express all these, but at the same time lets us probe into the intrinsic structure spanned by all these materials in the otherwise extremely high-dimensional space, so that we can extract meaningful constraints on the reflectance. So for that, we actually go all the way back and derive a novel reflectance model. And this part can be really dry, so I'm going to really skip all the details and still try to give you a high-level idea of what we do. Now, as you probably know, reflectance can be described with the bidirectional reflectance distribution function, or the BRDF, which defines the pointwise reflectance as the ratio of the outgoing irradiance to the incoming irradiance to one point source in one direction. And we specifically focus on isotropic BRDFs. And if you look at the reflected light distribution for one single incident light ray, right? So basically you look down on the hemisphere and strike the center of the base with one point light source and move that point light source slowly down to the grazing angle, you'll see that the reflected light distribution will roughly follow the perfect mirror direction and change its shape, right? And this complex behavior is exactly the source of difficulty of arriving at a simple analytical model. Now instead, if you use a simple reparameterization of using the halfway vector between the incident and accident directions, and again look at the reflected light distribution, it'll stay at the center and remain almost axially symmetric, which is a known fact. But our key idea is to view these as directional statistics distributions, which is simply to say that the intensity is going to be interpreted as a probability of seeing light in that particular direction. And without going into any further details, just to give you an idea for those who actually know about reflectance models, this new reflectance model has only two parameters for each of the mixture components, yet it can express all sorts of distributions. And for instance, if you take gamma to 0, it becomes flat in the angular space, which means it's Lambertian. And if you take gamma to infinity, it becomes a spike at theta h equals 0, which means it's a perfect mirror. And we can express anything in between by just changing these values. And we can also combine all these two-dimensional BRDF slices into one analytical model by applying functional PCA to the coefficients, the parameter values across different incident light ray directions. Now, all
theta there? What is the
theta d is the incident light ray direction. Theta h and phi h are the halfway vector.
So right now there's no geometry there. There's no such shape.
The shape is defined by the surface normal, which defines the halfway vector.
Oh.
Yeah. But all details set aside, what we end up having is an extremely compact expression that can express all sorts of BRDFs, and at the same time lets us actually extract out the linear subspace spanned by real-world materials in the otherwise high-dimensional space. So for instance, you can see that even in this extreme case of two-dimensional embedding of all these 100 BRDFs, we get these meaningful axes that the horizontal is roughly the amount of glossiness, and the vertical is the changes of the diffuse colors. Right? And that really means that we now have a very good handle, a constraint on the real-world reflectance, meaning that we can now recover the reflectance of materials to stay inside the space. In other words, we can recover realistic reflectance. And that's extremely important when we try to solve this radiometric decomposition problem. So let me actually show you how we use it. So the first problem that we focus on is the key problem towards visual material recognition, which is the joint estimation of reflectance and illumination from as few as a single image of objects of node geometry, right? And for now, let me assume that the light source is just a point source, okay? And the key difference from past methods is that now we have a very good constraint on the reflectance that we want to estimate. And we'll think about the probabilistic formulation, where we think that the image is generated by two random fields, one that encodes the reflectance at each pixel using that new reflectance model, and the other that encodes the illumination in the local coordinate frame. But because the surface normals are known, this is going to be a statistically independent random layer. But in any case, the key idea here is that we can now formulate the joint estimation of reflectance and illumination as maximizing the posterior of this factorial Markov random field, and we can now incorporate a strong constraint on the reflectance as a prior. So what we'll do is represent the reflectance with a new model, use the standard Gaussian likelihood, but the key is that we now can impose a statistical prior on the reflectance, which is a simple Gaussian in this case. And again, I have to emphasize here that we can get away with a simple Gaussian because we have taken care of all the nonlinearities by introducing this new reflectance model. Okay? So and with that we can do EM, and that actually amounts to doing an alternating minimization in the maximization step.
In this one, so you have reflectance elimination.
Yeah.
So the surface normals are within the elimination, or where are the surface normals?
Surface normals are given. We know the geometry. So and the surface normals will affect how these angles, the angles used for the reflectance and illumination are.
I see. So, but I mean, so you're saying you have an image, so it depends on reflectance, the property of the...
Right.
Object.
So I have an image, I know the geometry of the object, the reflectance property of that object and the illumination that's shedding light on that object are statistically independent.
Oh, I see. But the image will depend on the geometry, right?
The formed image, of course, is a result of all those three factors, but the geometry for now is no. So given those priors, we can estimate this with the standard EM approach. And what we end up with as an example result is just from the single image, we can recover the full BRDF, which means that we can always reproduce what that input image was like, which is extremely accurate, but at the same time, predict how this object will look like under different lighting conditions and from different viewing directions. Okay?
So from the vision point of view, isn't it a big assumption that you are assuming the geometry is known and then you want to talk about reflectance and illumination? Because the hardest problem is that you want to discover the geometry, right? That's the
that depends on which area that you're working on in computer vision, but I'll talk about geometry recovery too. Yeah. But, yeah.
What is changing in the estimated here?
So this is just showing you that we really do recover the full BRDF. So this is a rendering of the same sphere, and because we don't have much space, we're overlapping those spheres, rendered under different lighting directions.
I see. The light source remains the same.
or it changes.
So this is just a rendering to show that we really recover the BRDF. The only input image is this. And just from this image, we can recover all this information, all the necessary information to view this under different lighting conditions. It can be any lighting condition. Now, this is a simple example, so let's actually tackle a much harder and more practical problem where we try to recover the reflectance of a single object from a single image but made of multiple materials, right, like this mask. And this becomes an extremely challenging problem because now you have to figure out which pixel is which material, in addition to the fact that you have to recover the reflectance of that particular material from less surface normals, I mean angular samples. Now, for instance, this mask's forehead region is gold paint, except for this, this marking. But the algorithm actually needs to figure out that this entire region is the same gold paint despite the fact that they look very different, and at the same time recover the full BRDF of this gold paint just from this region, which doesn't have much curvature, right? Which means less angular samples of the BRDF. And we solve this with a multi-layer Mrf formulation. I'll skip all the details, but the key idea is that instead of just having one layer for one material, we have multiple layers, and for each layer we'll have an indicator value which says that only if that particular material's indicator value is max across all the layers, it can actually be responsible for that pixel, right? So it's very similar to doing layer-based optical flow estimation, but here we're estimating the materials. Okay.
And in this also you assume the illumination is known?
No, it's unknown. So we are estimating both the illumination and the reflectance. But I'm still assuming that the illumination is a point source. So we solve it, and just from the single image we can estimate which region is which material and estimate the BRDF for each of the materials. And we can re-render this so it looks very close to the input. And this is the actual indicator value. This is the hard segmentation and the soft segmentations and the corresponding materials BRDFs rendered under that point source direction.
when you do this multi-material detection, are you assuming you know the 2D profile of this mask?
We know the full 3D geometry.
Oh, you know.
Yeah, so we scan it. We scan it.
From no single image.
Oh, yeah.
But you already know the 3D model.
Okay, you can argue that it's not a single image.
That's what I was asking.
Okay.
But I mean, you will have something to say.
Well, you can. It's still a single image if you use Kinect.
But still, with the Kinect, you would have the depth data, right?
It's the same thing. We only have the depth data for this guy.
And but for Kinect, the surface normal extraction is not so accurate.
Right, so that's a good point. We can actually also insert a step where we refine the surface normal so that it's better explained, the appearance is better explained with those surface normals. So we can actually start with a fairly rough geometry that the Kinect gives us.
One more small question. I think you made a very good point about this top area. There's two small areas. They are same material, but it looks quite different.
Yeah.
Now, in your multi-layer random field learning algorithm, how do you, is any intuitive explanation you can differentiate these two small areas?
Well, first of all, it looks extremely different, especially because I'm showing you just a single exposure image. I mean, this is a high dynamic range image. So at this one exposure, this looks completely black, especially with this projector. But it does have some shading on it, which has the similar color to this gold paint. So that definitely helps for the algorithm to find it out. The intuitive explanation of how we actually segment it out is that we have each of these as different layers that we estimate. But these are the indicator values that are assigned to each of the pixels, which has a prior, on which we have a prior that encourages piecewise constantness, that also tries to preserve the color edges in it. So we are basically doing segmentation plus estimation with this layered approach. Does that make sense?
Is this like a white outlier? It's not outlier. It's more.
It's a highlight. Yeah.
This curves help? I'm just wondering.
Which curves?
You see that in this mask, you have a lot of boundary, like the wire, like a white.
These ones?
I'm just saying, are these white curves help with this segmentation, basically? That's what I'm.
Oh, maybe if we didn't have this white line, maybe it was more difficult to distinguish between the black and.
Exactly. That's what I'm saying.
Yeah, we weren't that careful to choose the object, but yeah, that might be a coincidence. Yeah.
It may be helpful.
Yeah, it might be. It might be. But of course, this is not perfect. I mean, but for instance, we don't recover this pink region, right? But that's almost flat, which means that we almost have one angular sample for the Beardew. So you can see how tough this problem is. Remember that we only have the single image to recover all this information. And then somebody might argue that, okay, why do you stick to a single image? And we're just trying to push the boundary what we can extract from a single image. So we can, of course, include more images. For a single image, we get this result. If you have another image taken on the slightly different light source direction, we can get a better result. And you can see it's a little bit more crispy than crisp than this. And the segmentation now includes this region and so on. So the accuracy can become much better as we increase the number of input images. So that's a single object, multiple materials, but we can also think about cases when we have a single scene made of multiple objects of different materials, right? So for instance, from an image like this, we can now segment the scene into different objects of different materials, right? And that might be a more relevant scenario for instance robotics, where you want to grasp and tell the robot to actually grasp the apple despite the fact that in shape it looks very close to an orange, right?
So suppose in this case, so you know that in this image there is a spherical object, right? You know the shape and then you know the result.
For this we also know the geometry and we just scan it.
Huh?
We scan it with a laser scanner.
Oh, I see. So you have a laser image also.
Yeah.
Okay.
So it's like a homemade Kinect. We have a laser scanner and the camera calibrated together. Okay, and we can recover the full BRDF for each. Now, that was all done for a point light source. So let's actually try to take this outdoors. So instead of trying to estimate the material as reflectance and the illumination as a point source, let's try to estimate the illumination as arbitrarily complex natural illumination, right? And this will significantly broaden the possibility of generative visual material recognition. But at the same time, it's a small change, but a really dramatic departure from the conventional laboratory settings that we are so used to in physics-based vision.
So if you have the depth image,
yeah.
Then have you guys tried to segment the depth image? Don't do all this reflectance, and compare the results that whether this reflectance is helping you significantly.
Oh, we haven't done a comparison. You mean a segmentation based on reflectance versus segmentation based on purely geometry? We haven't tried that. But we can always come up with a way to, I mean, for the mask case, there's no way that you can actually segment it based on the geometry, right?
What about using both, like?
Yeah, I think that's a hybrid will definitely help, yeah. Yeah.
Okay.
So the key behind this talk is that we have this material information encoded in the images. Why not use it? And it will definitely supplement any algorithm that's already used, right? Purely on geometry or whatever. So in any case, let's really try to take it outdoors, but we now have to deal with this thing, right? And this is a spherical panorama of natural illumination, and it has so much complexity. It's not even outdoors, it's just the indoor kitchen scene, but it has so much complexity, which is directly the burden on the algorithm that now needs to actually recover this in addition to the full BRDF just from this single image, right? Now, but if you think about it, the natural illumination shouldn't be something that you completely resent in this scenario, because it actually carries some structure in the distributions of the pixel values in the intensity and the color, right? So the question is, how do you actually exploit that structure of natural illumination? Now, one thing that you can immediately come up with as an idea is that, okay, natural illumination is just a wide-angle view natural image, right? You stick a camera at the center of the object, looking inside out, and pan around and take a spherical panorama, and that's your natural illumination, right? Which suggests that we should be able to leverage the statistical characteristics of natural illumination, just like natural image statistics, right? So in fact, if we compute the gradient distribution for many spherical panoramas, it turns out that alpha is about 1.2, 1.3, suggesting that you have a long tail distribution for the gradients, right? So that definitely can be a good prior on the natural illumination. But there has to be something more. Right? And for that, we can think about how the reflectance acts upon the illumination. So if, for instance, if you have a perfect mirror, the natural illumination is going to be directly reflected into your eyes. But if you have something that's more matte, a reflectance like this, the natural illumination is going to be angularly blurred in the local region and pasted onto the surface of the object. In other words, it acts as a bandpass filter in the frequency space, right? Which means that it's basically doing angular blurring, right, of the natural illumination as the reflectance becomes more matte. Now, what does that mean? That basically means that if you look at the histogram of the input image, it's the histogram of the natural illumination locally angularly blurred by the reflectance. And because that blurring generates in-between colors of the distinct original natural illumination, the histogram is going to be spread more from the original histogram of the natural illumination, which means that the reflectance acts in a way that increases the entropy of the histogram of the natural illumination, which in turn means that you should be recovering the natural illumination to have lower entropy, right? And that can be a really strong prior on the natural illumination, which we can encode by computing the continuous histogram so that we can take derivatives, and then by imposing a negative entropy plot prior. Okay? So armed with those two priors on the illumination and the strong reflectance prior, we can solve this again. And from a single image, we can estimate the full natural illumination and the full BRDF like this, which lets us predict how this object looks like. It is very accurate, not just under this illumination, but from different viewing conditions and under different lighting conditions. And even predict how other objects with reflectance characteristics lower frequency than the original would look like. Now, one thing you notice is that this doesn't look as good as the ground truth, right? Now, remember that the reflectance acts as a bandpass filter in the frequency space, so there's no way that you can actually recover all the high frequency details of the original natural illumination. You can only recover the frequencies up to the ones that were transmitted by the reflectance, but you still see that it really captures the gist of the natural illumination. Like it captures all the dominant light sources, their spatial distributions and colors, right?
So this ground truth, I mean, how do you, what these images are ground truth, how do you get that ground truth?
These are synthetic images.
Oh, okay.
So these are panoramas and materials from the mole data set.
Oh, I see. So when you say this now natural illumination, so you are, so it doesn't, it goes beyond the single light source.
Right. Anything.
Anything, and then what are you computing in terms of? You're computing many light sources?
No,
light sources?
an image, a spherical panorama.
And that is this illumination
Yep.
image?
Yep.
And tells you how much light is
In that direction.
that pixel?
Yeah. So you can think of this as an environment map. It's a sphere surrounding that object.
I see.
Yeah.
Okay. So that's more explicit, more finer information compared to old model. This is just one light source.
No, it's not a. Yeah, it's not estimating multiple point sources. It's
Yeah.
really just the whole image of the surrounding.
And that says that at this pixel, how much light is coming
Yeah.
or where it is coming from?
Right. Both.
Both?
Yeah.
So each pixel has how many numbers do you have? 3, 4 numbers?
This is an RGB high dynamic range image.
I see.
Yeah.
So you have 5, 6, each is a vector, like how many numbers? 10?
It's an RGB floating point value.
Okay, so 3 numbers.
Yeah, yeah.
I see.
Yeah.
Okay.
You had a question?
Yes, I guess my question is related to Dr. Shah's question. Because I was going to ask the natural illumination prior you're using to do the recovery. Are you using the same prior for any objects, or you use multiple? Depends on the location.
We use both gradient distribution and less entropy prior on the illumination for any image.
What I'm saying is like the prior you're using, because to deal with this multiple source, point source situation, and are you assuming you use a single prior for the whole recovery, or you use an individual a little bit different prior?
For different images, is it different or it's the same thing?
Yeah.
You just use one prior.
I guess that's all.
It's the same prior.
So if you change the same, you're using totally different prior, right? Suppose right now you're doing this estimation. Now we change it to a picture taken from another kitchen
Yes.
with more lights.
Right.
Are you going to use a different prior?
No, it's the same.
It's the same?
Yeah. The prior is to just reduce the entropy to recover the illumination to have lower entropy than the input image. And that intuitively just simply means that let's try to recover the natural illumination to have as distinct sets of colors and intensity values. And it's a global prior. It's not like an MRF with spatial clicks that says that let's try to be piecewise constant. So it's an extremely strong prior that tries to recover the illumination like this. And that has no parameter at all.
So you're saying like adding more lights doesn't change anything?
No, no. Any illumination is the same.
You're taking a fairly tiny object.
Yeah.
So you have shown that different types of reflectors.
Yeah.
Do you have any other?
We have run this on 100 BRDFs that spans from almost purely diffuse to almost perfect mirror. And you have a very good question, is that remember that the natural illumination can only be recovered up to the frequencies transmitted by the reflectance. If the reflectance, the object becomes really dull, matte, that means it's a really low frequency filter. So all the information that you can recover from that is going to be much more blurred than this. Which is natural, right? If you have a mirror, you get a perfect reconstruction. Yeah. Any other questions?
So this ground truth is from the center of the image, object?
The ground truth is from taking an image of a spherical ball. Oh, did that answer your question?
Yeah, I mean, if the camera is in the center of the object, then...
Oh no, we're not taking a panorama. This is a environment map that Paul Devebeck took when he did the HDR imaging of environment maps. It's publicly available, and we use that to render these input images. I'll show you real results later. One more thing that I want to add is that we have to also consider this color constancy problem, which you might be familiar with. That is the fact that if you have a green-looking object, you really don't know whether it's a green reflectance plus white illumination or a green illumination plus, what did I say, white reflectance, right? So we just simply fix that by saying that, okay, on average, the illumination has to be gray. Okay, so any bias in the natural illumination color will appear as a color shift. But the key is that you really see that the characteristics of the reflectance is recovered very accurately. Here's another example, right? And you can see that we recover the full BRDF from just this single image. Okay, and we can really take this outdoors. From each of these single images taken under 4 different lighting conditions, natural illumination, we can recover the natural illumination and the full BRDFs. And if you close your eye to these color shifts coming from that ambiguity in color constancy, you can see that we can recover the characteristics of the BRDF very accurately because they agree very well. And both of these will allow us to predict how this object will look like under this illumination or different directions. And also you can see that the recovered natural illumination is really capturing the gist of these actual illuminations, right? Here's another set of examples. You can have these complex shapes. Of course, we are assuming that the shape is known. And we cover the BRDF and the illumination, which capture the illumination pretty well.
So when you show those circles,
yeah.
the spheres and then so on, so can you explain what we are seeing there? So what is this?
So from this single image, we recovered this and the full BRDF. So the full BRDF means that for any direction of light source and any direction of viewing direction, we can predict how that pixel is going to appear. So we can render a sphere with different light source directions. So this is just to demonstrate that for one profile of illumination directions, we can tell how that object would look like, even for grazing angle illumination. Okay. So we can really use, if you're familiar with it, we can even use just an apple whose reflectance we have no idea about as a light probe to actually get the illumination like this. And that will be useful for predicting how other objects would look like, which can be used for scene understanding and tracking and so on. Okay? And then the question is, okay, I'm assuming geometry, and that's sometimes a no-no for some people in computer vision. But of course, we are working on the estimation of geometry, and here we've done some work on joint estimation of reflectance and geometry under known but complex natural illumination. Okay? And I'm not going to go into any details of this, but the idea is pretty much the same. We exploit the structure of natural illumination and the strong prior on the reflectance. So from a single image taken under a known lighting condition, we can recover the surface normals and the depth values from it. Okay? And it does a decent job. This is shape from shading on the natural illumination, right? And it turns out that you might think that going from shape from shading on a point source and going into the wild makes it more difficult, but in fact the structure conveyed in the natural illumination is actually reflected inside the image, which lets us, for some areas, accurately estimate the surface normals.
So this model, is helping you to better shape from shading?
Yes, yes, for arbitrarily reflectance. So it's not Lambertian. Yeah, definitely.
And so the illumination is important because the simple model is simple one single light source, and they will. But these kind of objects will it matter? Like this is a very simple object, is it right? So if you use a standard, model of single light sources, you could still get something reasonable.
If you rely on some really strong priors on the geometry, like, okay, let's try to make it really convex. Yeah, everything will try to become a sphere, and if you have a spherical object, it will accidentally become very accurate. But I think the key here is that we have come up with a way to jointly estimate both the reflectance and the illumination by exploiting the structure of the illumination on one hand, right? And the other, we have this method to jointly estimate the reflectance and the illumination. So we kind of want to combine these two. And of course, recovering all three from a single image is a really tough task. But if we have, my belief is that if you have some rough initial geometry estimate to begin with, we can kickstart the process to iterate through to get better results.
So how much like the reflectance, or how much the illumination, this more sophisticated model, is helping you to recover the shape? Like,
in terms of geometry, having a more complex illumination like this natural illumination definitely helps than having a points loss.
That's right.
Yeah, because you have more structure reflected off that geometry, which you want to kind of pinpoint the orientation of, right?
So for recovering just if you're interested in recovering just a geometry, then this model may not be that important. That's what you're saying.
No, the reflectance model and the prior that it gives us is definitely important for any case when the reflectance is not known.
Okay.
Right.
So this involved illumination model is really important if you want to do the depth estimation, shape from shading.
Yeah.
And reflectance is important.
Yes, definitely.
Both of them.
Yeah. Everything we derived is definitely important, if you're asking.
So you said that given the illumination, then you can derive the geometry. So what do you mean by giving the illumination? Because you can as well, like the does put a sphere there, while you're taking photographs, put a sphere and capture the illumination.
That's what we did here, yeah.
That's what, so basically, in any scene, you can go out with a camera and all that one, and so you can actually extract the geometry, extract the BRDF and dump, right? Is that, basically you put a sphere there, mirror sphere, and capture the environment. So everything, all information you have. So is it?
Oh, wait a second. Cap, by the way, this is not the end of my talk, so I can probably answer that after I go through the second part. So let me switch gears and talk about, maybe this might resonate better for people who are interested in machine learning and so on, or high-level object recognition or scene understanding. So in this discriminative material recognition approach, we want to classify each pixel into different materials, right? And I should point out that this is very different from recent work on scene understanding based on scene recognition based on attributes, because we're trying to recognize materials at each pixel. And it also kind of subsumes texture recognition, because texture really is just one aspect of how a material appears. Now, there are two past methods that tries to do discriminative material recognition at the image level or object level. But these methods heavily rely on object shape cues, right? Or object information, like extracting the occluding boundary and computing the features across and along them. Now, our ultimate goal is really to recognize the material so that we can use it as a context to help high-level scene understanding, including object recognition. So we really don't want to rely too much on object information, right? So the goal is to do discriminative material recognition at the pixel level without knowing and using much about the information of the geometry, object. Now, that's much harder than said, for instance, for two reasons, right? Now, one reason is because there's a huge interclass variability in the material appearance. For instance, all these images are objects made of plastic, right? But they look so different because of the ways that they're instantiated, the shapes, the colors, the environments, and so on. And the second problem is that, even worse, we don't know what makes all these look plastic, right? We don't really know what we should make the computers to look for, the features, to recognize them as plastic, okay? Now, but if you really think about it, there has to be some information, because we can actually tell that these all look plastic, right? And if you think about it, we can recognize these as plastic made, because we know that plastic has these properties, inherent properties that are sometimes directly exhibited in the appearance. Like plastic tends to be smooth, it tends to be translucent, it tends to have this man-made look to it, like maybe because of these vivid colors, right? So why not we try to actually represent these materials based on those traits, okay? So what we propose is to introduce a novel intermediate representation for materials that we actually try to learn, okay? So what we are trying to say is that represent each material as a combination of the probabilistic presence or absence of these certain material traits or properties, right? And these traits can include, of course, these visual properties like shiny, but also include non-visual ones like tactile ones, like smooth and rough and so on. So what we're going to say is that, okay, fabric is fuzzy or woven but cannot be hard or metallic, right? Metal can be shiny and smooth but cannot be fuzzy, right? Those are the things that we want to, that's the way we want to represent materials. And the goal is then to recognize these materials at every single pixel. For each pixel, we want to tell how fuzzy that is, how organic that is. Okay? Now, to give you a little better idea of what these visual material traits that we're trying to recognize are, these are the local patches centered around each of the pixels that were actually recognized by our method as having that trait. Okay? So we defined 13 visual material traits from shiny to organic, and you can see that you can kind of get an idea of what I'm talking about. Shiny is often characterized by having all these highlights passing through these local patches, right? Fuzzy has this really fuzzy look to it. There's no other word that I can come up with. But it has this fuzzy look of like wool, right? And organic has these typical colors of organic surfaces and texture patterns like a leaf, right? And one thing that you notice is that these traits are not mutually orthogonal, right? Fuzzy and soft definitely share a lot in common. Metallic and liquid look a little bit similar too. So you get an idea, right? So now, how do we actually recognize these? Now, as I said, we have no idea what kind of features we should be looking into, right? There's this sift and jets and so on, but these are nice features that were invented to encode the shape cues in a way invariant to the appearance variation, right? So we'll try to actually just learn the features that are best suited to represent these visual material traits. And for that, we'll actually just learn the local appearance basis of visual material traits by using a sparse convolutional autoencoder, which simply means that grab a lot of patches from the training data, dump it into this equation, which we try to minimize, and learn these convolutional filters that minimize the reconstruction error while satisfying these constraints that says, don't be too big and try to be spatially sparse. Okay? So we end up feeding 32,000 32 by 32 local patches into this optimization and get 128 7 by 7 convolutional filters as the basis, which will serve as the features. And you can see that if we actually sort these kernels based on the frequency they fire for each of the different visual material traits, you can see they actually try to represent the characteristic appearances of these traits, like soft and liquid are checking for the presence or absence of these complex gradients in local regions, whereas smooth and organic are checking for the presence or absence of these bigger gradients. Now, one caveat of this learned unsupervised features is that they cannot, because it's a convolutional filter, they cannot express nonlinear operations. So we just supplement that with the usual gang, the hog and LBP and color histogram and so on, and then just feed it into a group-wise feature selection method, which amounts to just preparing a lot of classifiers with different combinations of these feature sets. In our case, we use a random decision forest and pick the one that gives the best accuracy. So what you end up with is a classifier for each of the visual material traits using the best combination of these features. And you can see that actually all the features are used almost uniformly across all the different traits, suggesting that all of them are actually important to span the space of all these traits. Okay? So for each pixel, we can compute the probability of that pixel having that trait or not, right? We can just threshold that by 50%, and this is the accuracy. And remember that this is done independently for each pixel, so these are not one versus all, right? It's not exclusive, and still we can get on average 80% accuracy to recognize these visual material traits. And some of them are actually hard, right? For instance, translucent and metallic are the harder ones, and that's understandable because metallic surfaces and translucent surfaces, the appearance is defined by the surrounding, right? They just reflect or refract. So even in such cases, you can get higher than chance recognition results.
So how much difference these the standard features make compared to the deep learning you have?
We have a list. Don't have it in a slide, but
I was expecting that they should do it. You don't need to use this HOG LBP.
It helps a little bit to increase the accuracy. And for some of them, for fuzzy, for instance, well, you can think of we actually separate the unsupervised one into oriented and non-oriented one. But for some of them, it's not in this list, but some of them it makes more sense to actually check for, like man-made is often characterized by the surface markings, which are better characterized by, for instance, hog, than just looking at the texture with these unsupervised features. Okay, so for each pixel, we can tell the probability of what that, the likelihood for each of the traits. So for any input image, at every single pixel, we can compute the probability of that trait. And then just here, I'm just showing you the pixels that have higher than 50% probability. And as I said, it's not mutually exclusive. So this fur can be both fuzzy and soft, right? And the bear has a rough fur, and the water is liquid, right? I'm just showing 2 each. I'm here showing 3 each. The buildings are man-made, the grass is organic, and the cloud is translucent, and so on, right? And remember that, of course, this is noisy, but remember that we are doing this recognition at each single pixel independently, right? So if you want to, you can impose any spatial structure to it using whatever MRF or CRF if you want. Do you have a question?
So when you use LBP, that actually captures a little bit of neighborhood pattern.
Mm-hmm.
So, I mean, I was just wondering, like, if that could be, since you're using that, feature selection criteria, that could be integrated before, and then you can still have the advantage of using the neighborhood information.
What do you mean integrate before?
So what I'm saying is, you are doing it on a per pixel basis, right?
Yeah.
So, but using also with the per pixel basis, you would have the neighborhood information that is coming from the LBP. So,
well, we're doing the recognition per pixel, but the recognition is based on the local patch surrounding that pixel.
You also are getting an area.
Yeah, we can't really just do it on really one pixel. It's a patch around that pixel, but the decision is for that center pixel. Yeah. Okay, so now we have this great way of finding the traits for each individual pixel, and that gives us rich information about the material, so we can think about using it for higher level, extracting higher level information. And one natural thing is to recognize the materials from the traits. And if you actually compute these class conditional probabilities as histograms of these traits for each different material, you can see that they actually carry some really interesting discriminative information. For instance, it says that plastic is often smooth, rarely rough, sometimes organic, and somewhat soft, right? And this, of course, doesn't necessarily mean it's physically correct. For instance, it says stone is often soft, right? But that's not true, right? But porous stone can have a soft appearance, right? So these class conditional probabilities carry really good discriminative information, so why not just concatenate all of them, strip it out as one feature vector, and throw it into SVM with a conal intersection, histogram intersection conal to recognize the materials, and that's what we did. And these are the confusion matrices for the two data sets used in the past two methods, and it turns out that we achieve 49.2% on this Flickr data set and 60% on this ImageNet data set. And for this data set, Sharan et al., who did this method, they get 57%. And that's much higher than our 49%. But they heavily rely on object information. Like, as I said, features extracted along or across the boundaries of the objects. Right? And if they don't use that, they can only achieve 42%. So we clearly have the state of the art for the local recognition. And I have to reiterate the importance of recognizing materials regardless of the object. If you try to do it in the product space of objects and materials, you have to consider all the combinations. And if you have a new instance that doesn't lie inside that product space, you're doomed, right? But in our case, we are independently recognizing the materials. Okay, and some failure cases. You can see that these are really difficult cases, like the stone is recognized as wood and the glass is recognized as plastic, and they do kind of look like wood and plastic. And this failure case is just coming from the fact that the bounding box is not really hugging the object of interest, but has this background paper in it. Okay, now we have a way to recognize the traits at each pixel, also even extract the material. Why not we use it for some scene understanding task? So the simplest thing that you can think of is to use it for image segmentation. So we took normalized cuts, the conventional method for image segmentation without any parameter tuning, ran it on these images, got these results. Then we computed the visual material traits, right? And then introduced a new similarity measure based on those traits by just exponentiating them, and run the same normalized cut and get these results. And now you can see that because of the difference in the materials, you can extract out these interesting regions. Here's some more examples. Without the material traits, it's really having a tough time finding out where the deer is, but now we can extract it out. Okay? Now, one last thing. Using the material traits, we can use it to help object detection, which is, of course, a central topic in computer vision. When we train the classifiers for the object detection, for each of the bounding boxes, we can compute the material traits, and then train another classifier that checks whether that bounding box that you detected has a visual material trait distribution that conforms to that object that you're trying to detect, right? Which lets us call false positives, which is a real headache for object detection. So here I'm showing the successfully called false positives in green boxes and the successfully preserved true positives in blue. And you can see, for instance, the horse detector keeps on saying that the sheep are actually horse, but the traits tell us they aren't because the fur is different, right? Okay? So to summarize, I talked about two distinct approaches towards visual material recognition. One is a generative approach where I introduced a new reflectance model to extract a really strong statistical prior based on the space of reflectance so that we can do radiometric decomposition in the wild. The second approach was a discriminative one, where we tried to directly tame the appearance of materials by introducing this intermediate representation called visual material traits. And I demonstrated that we can even recognize the materials and also use it for higher level image understanding tasks by using it as a visual context. And really, the take-home message that I wanted to convey is that we really should be looking into extracting and exploiting this rich material information embedded in the images. And for that, we sometimes have to solve these severely ill-posed problems that require some really careful thinking about how to tame those variables. So I hope this will inspire you to do some research in this area. And to facilitate that, we are releasing all the data and code at least for the first half for now, and for the second half we will try to release it as soon as possible. And we as a group do a lot more, as Dr. Shah said. Video analysis in really crowded scenes, tracking a lot of people like this, or 3D geometry processing, like in introducing the scale space of surface geometry for 3D object recognition in real clutter, or non-rigid image registration that fully automatically latches on the local structures while minimizing the global shape difference, to applying them to other domains like digital archaeology, where we semiotically try to reconstruct broken vessels excavated from some digs. So I hope you can visit our website and check out some of these projects. And with that, I would like to conclude. Thank you for listening.